Has anyone converted this to a problem with integer variables instead of rational numbers? What did you get?
So I just rewrote it as like x over a squared plus y over b squared equals 3.
Good point. Good start.
So then they're all integers.
Yeah.
And I solved it down for y, and I got y equals b over a times square root of 3a.
Oh no square roots. Square roots are hard. I don't like square roots. Keep it polynomial.
Oh, then
don't do square roots. Square roots are very, very confusing number theoretically. The square root of a rational number could be a rational number, could be an irrational number, who knows? So let's not go there. So one kind of good general approach to do is like, okay, so x and y are supposed to be rational numbers, right? So we can write them both as a over b and c over d. One thing we should do maybe is just use the same denominator. Like we can assume that like we can bring them to a common denominator if we want to, right? We can assume that they're both something over n. Okay?
Please. Sorry.
Or if you don't like it, let's not do it. Let's just say a over b squared plus c over d squared equals 3. Just multiply out by the denominators, right? So this gives me AD squared plus BC squared is 3BD squared. Do you guys agree that this is the same thing?
Yeah.
All I did was multiply out by B squared and by D squared, right? And I got this. Now, I have 4 variables here, but not really, right? Because, well, I have some whole number squared here, plus another whole number squared here equals 3, some other number squared. So let's just invent new variables. Let's call this capital X squared plus capital Y squared is 3 capital Z squared. Okay? So let's just agree that if this cannot be solved in whole numbers, there's no way this can be solved with rational numbers. Are we cool with that?
Yeah.
So this is the version, the whole number version that I was referring to. That's the general procedure. You write down your rational numbers as fractions, you clear the denominators, you just give them your names. Sometimes going backwards is a little bit tricky because of all this liquidity, but it doesn't matter. If this doesn't have a solution, so it doesn't matter. Alright, so why can't the sum of 2 whole squares be 3 times a square? There's at least 2 ways to do this. One is with residues modulo 3, and one with residues modulo 4. What do you prefer?
3.
Okay. Wait, sorry. Question? Okay. This number is divisible by 3. Therefore, that number is divisible by 3 as well, right? How do the squares behave when we look at the residues modulo 3? Let's just look at the square numbers. Here are the square numbers: 0, 1, 4, 9, 16, 25, 49, etc., etc. Let's just check the residues modulo 3, okay? What is the residue upon dividing 0 by 3? 0. 1.
1, 0.
Anybody see a pattern?
Yeah.
What's missing from this list?
2.
What is 2? Is there a 2?
No.
Well, you're saying no just because you see a pattern. Why is there no 2?
Oh.
What's wrong with 2? Where is it? 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. What's wrong with 2? No 2. How do we prove that the residue upon division by 3 of any square is either 0 or 1?
Just write it out in mod.
Sorry?
Well, because you write every number as a representation as 2n plus 1. Or
3.
3, sorry.
3m plus something,
Yeah.
right?
Either
So
0
if you're not sure about, one good way to do this is just write it as 3. Every number can be written as 3n plus j, where j is either what?
0, 1, or 2.
0, 1, or 2. Every number can be written to 3m plus j with j is either 0, 1, or 2, right? Well, let's square it. What do we get?
9m squared
9m squared
plus 6mj
plus 6mj
plus j squared.
plus j squared. Perfect. What is the remainder of that when we divide it by 3?
0.
0. This is divisible by 3.
0, 0.
What is the remainder of that when we divide it by 3?
0.
What about this one? J squared. I don't know. Let's see. When j equals 0, this is 0 squared is what?
0.
0. When j is 1, we get.
1.
When j is 2, we get
1.
4, which is the same as 1. The residue modulo 3 is 1. Right? So whatever j is, 0, 1, or 2, the residue is just 1. There's no way to get a residue of 2. Another good way to see this is just to work modulo 3 in your head. And then I don't know if anybody's talked to you about this stuff, but like, you can forget about the fact that there are whole numbers and just let's imagine that everything in our world is 0, 1, 2. That's it. And let's do math in 0, 1s, and 2s. So 0 squared is 0, and 1 squared is 1, and 2 squared is
1.
1. Because in this arithmetic, that's what you get. When you just ignore 3's. Ian Stewart once wrote a piece about like you have this glasses and they don't see 3's. Whenever you have the, like they're invisible. You have one apple, you have another apple, you add another apple, you still see anything. It vanishes. Like if you have those glasses on, all 3's are gone. 2 times 2 is 1. 2 plus 2 is also 1. Right? And this arithmetic modulo 3, that's, and those are the squared, that's it. 0 squared is 0, 1 squared is 1, 2 squared is also 1. Let's take a break.
I have a geometric proof. If
Okay.
you want a square, and you want to divide it by 3 and take the remainder,
Uh-huh.
what you do is you just put a cross through the middle of it and pull out the corner.
Super.
So then if you keep doing that to any square, you're either going to have just the last corner left over, which is one piece, or you're going to divide it evenly by 3, in which case there's no remainder.
Fantastic. I'm not sure everybody's convinced, but that's a great point.
Say that again.
You take a square, like a square of dots, and that's a square number, and when you want to divide it by 3 and take a remainder, you can just cut it into quadrants, pull off the corner, and then you take that number and cut it into quadrants and pull off the corner. Eventually you're going to have
What
one
if the
piece.
side length is odd though?
If it's odd, then it will divide evenly by 3.
No.
Mm-mm.
No. If it happens to be originally evenly divisible by 3, it will.
Not like
But no,
5 by 5.
I think the point is, in the end, what are you going to get in the end? Like, you start with some square array of dots, right? You said do this. So there's, these are divisible by 3.
Right.
So you get, oh, I see. I'm sorry. Right.
But it doesn't work
If it's even,
Right,
you're okay.
I'm sorry. The only one's
Ah,
okay. I'm sorry.
okay.
I missed that.
Make this work.
Thanks, Josh.
Because
Almost
you
a
can't
good
divide it into quadrants.
Almost a good proof.
It's not-
Um,
I mean, if it's even, you can't.
You know, let's not take a break. Let's just finish this and we'll get back to this later. So, upon division by 3, this is what? This leaves a remainder of what? 0. What about these two? This can be what? 0 or
1.
1. This can be what?
0.
0 or 1. So 0 or 1 plus 0 or 1 is 0. So what do these have to be? Can any of them be 1? If we had a 1, 1, we would get a 2. If we had a 1, 0, we would get a 1. 0, 1, we'll also get a 1. So they both must be zeros. But if these two are zeros, then these squares are both divisible by 3. Right? The squares are actually divisible by, if a number is divisible by 3, its square is actually divisible by 9. So the sum is divisible by 9. So this is also divisible by 9. So z is also divisible by 3. I should have said this before. But we could have assumed initially that these numbers have no common factor. You know why? If they had a common factor, what could we do then? Just take it out. If all of x, y, and z were divisible by 7, we could just cross out the 7 squared from everything. If all of x, y, and z are divisible by 3, just cross out the 3 and keep going. In the end, we've got to be in a position where x, y, and z do not have a common factor. But we just saw that they must all be divisible by 3. Otherwise, this doesn't work. just show that they are all divisible by 3. Divide them by 3, get a smaller solution. And keep doing this. You get smaller and smaller and smaller solutions in integers to an equation. This cannot happen. The integers eventually get stuck at 1. Right?
Or you could say, suppose we have the smallest solution.
Yeah. Find the smallest z solution. The small solution in terms of z. Find the solution that has the smallest z. Well, we just showed that both x, all of x, y, and z must be divisible by 3. Divide by 3. And here's a smaller one, contradiction. And let's you think about this over the break. We have lots of other stuff to do. So, what do you guys need? We have an hour. Because we figured out a new formula for the circle, which is kind of useful for a variety of purposes. And we also talked a little bit about diaphanty analysis, meaning this field of math where we are given a polynomial equation and we're asked to solve it in integers or in rational numbers instead of just complex numbers or real numbers. And the one thing I want you to take away from this is that solving equations in rational numbers is way harder than solving equations in real numbers. It's kind of confusing. It's kind of backwards. See, the rational numbers are simpler, but rational numbers are much, much harder to deal with when we're solving equations. So here's another equation. Pretty famous one. The main difference between this equation and the ones we worked with so far is that this one has degree 3. So we're out of the realm of conic sections. This is not a circle, not an ellipse. This is something else. Confusingly, it's called an elliptic curve. But it has nothing to do with ellipses. Well, in a very convoluted way, it has something to do with ellipses. That's why it's called an elliptic curve, but it's not an ellipse. We'll draw a picture of it in a second. But first thing, can you find any simple solutions for this one? Rational or integers? Integers is even easier to.
2
How about
and
negative
5.
1 and 4?
X equals what? Sorry.
Negative
X
1
equals
X
2.
Wait.
and y equals 4.
What else?
X equals 2 and y equals
2.
5.
Yeah. So if x is negative 1, then y is what?
4.
4. Yeah. Great. If x equals 2, then
Y is 5.
y is 5. What else?
X equals 3. 27, 40. No.
Any others? What about negative 2?
3. 3.
Works?
Yes.
Oh, yeah.
3. Any others? What about 4?
10?
81. 9.
9. Wow. See, this seems to kind of work. This equation, uncharacteristically for many equations of this kind, has a pretty good number of integer solutions, right? Making sense of this set of solutions is really, really hard. And many years ago, there was a guy called Bachet. I think it was called something Bachet de Eziriac. And we're talking early 17th century here, way back. And he noticed the following thing. If xy is a rational solution, to this one, then so is
It's an interesting thing to notice.
look at this. So this is exactly the point I'm trying to make. This is an amazing thing to notice. You don't just walk around and go, whoa. So is x. So there's some y here. Well, figuring y is not hard. If I give you an x, if I give you some x value, and I guarantee you somehow magically that this x value is going to work then figuring out the y is not really very challenging, right? You just plug the x. Just like when I said x equals 4, it wasn't really hard to figure out if y equals 9 is the answer, right? Let's see this in action, for example, for a second. Let's try. Do you guys have calculators?
I have one down the hall. Should I run it?
Like, what? A few calculators are going to be enough. We're going to believe you guys. So let's use Bachet's formula. Let's start with, I don't know, let's start with x equals -1. What is the new x? So please do me a favor. Plug -1 into that thing and tell me what you get.
That's a 4 in front.
Yes, it's x over 4 times x cubed minus 126. My math here? No, I'm sorry. It is one. I was right initially. 136. I apologize. It's not going to work with 126. I swear to God. It's not going to work.
Alrighty. What do you want? What value of x you want?
Sorry, I'm trying to get what is, if x is -1, what is this? Oh, you have programmable calculators.
Yes,
Fantastic.
Oh, good. Well, let you just do it.
What'd you get? 137 over 64? That looks right.
937 over 64. Yeah.
But,
Divided by 4.
let's see. Yeah. Yeah. That looks right.
I'm sorry.
Okay, so can somebody now, again, I'm sorry, my mental math is not good enough. Can somebody please cube that thing? Add 17, hit the square root button and play.
Cube it. Add 17.
Yeah. Well, what I really need to know is if the result is a rational cube, a rational square.
I don't know, so you want me to square root that?
No, don't. Tell me what this is. As a fraction.
After, okay, 7027801 in the numerator, in the denominator, 262,144.
So this is a square. I know that. This is.
So that's the cube.
This is to the 18.
That's just the
That's
cube
the cube
of
plus
it, right?
17. Oh,
no,
did you add
that's the
17?
plus 17.
Oh, plus
I already
7.
added the 17.
Oh.
Okay. So this, I know this is a square. Is this a square? Please.
Yes,
Ah! Okay.
2651.
2651 over
512.
512 squared. Magic. So let's just repeat what just happened here. We guessed a rational solution of this equation. We just guessed one. X equals -1, y equals 4. We took a formula found by this guy in the 17th century. The formula says the following. If you have a solution to a certain x, I'm going to give you another solution with another x. This x. Now, I have to impress upon you that if you just take any random rational number here as x and you cube it and you add 17, usually you're not going to get square. Usually this is not going to work, right? Just take any random number, 5. 5 cubed is 125. Plus 17 is 142. Does this have a square root? No. The square root is not rational, right? And this is what happens typically. Here, magically, we started with -1, which is the solution we guessed. We called old Mr. Bachet, and he gave us this other thing, which is a crazy fraction, 137 over 64. And magically, this x, if you cube it, you add 17, you take a square root, you get a rational number. So this is another rational point on our elliptic curve. Now, as far as we know, when Bachet found this formula, he really did it by magic. I don't think anybody knows how he did that. In reality, there's a very, very simple explanation to this formula, which Bachet had no way of knowing because he never did that. He You never did geometry. So I want to show you what this
So
is.
isn't it supposed to equal to 4?
Sorry?
Isn't it supposed to equal to 4?
What's supposed to be before?
No, you get a different solution with a different
Getting
one.
a new
Oh, I'm sorry,
rational solution.
These are just random points that we have discovered.
Yeah, but if you plug in -1 in that formula,
Yeah.
isn't it supposed to equal 4 still? Because then
Right, but we plugged in 137 over 6.
No, I'm sorry. So this is what the Shea formula does.
Yeah,
It
no,
gives us.
yeah, I figured it out.
Okay. The y, I'm not telling you what. There's a formula for y as well. It's not very important because, again, once you have the x, you can figure out the y fairly easily. It's not the same y. It's a
Yeah,
different
no,
one.
I get it.
Okay. So a couple of things I want to show you now are, first of all, what do these things look like? Anyone guess what this curve looks like? So what does x cubed look like? What does x cubed plus 17 look like? Same thing, only higher. And now we take the square root. So this is x cubed plus 17, or something like this. Right? When we take the square root, what happens? What happens to the left of this point?
Goes away.
Nothing. No square root. And to the right, we just shrink it by something, right? The square root just makes it smaller. So it looks something like that.
Wait, shouldn't it still intercept on the
I'm
left
sorry,
side?
of course it doesn't touch the axis here. The x is somewhere here, and this is going to be around 4, right? So let's see what happens. This is like square root of 17.
Right.
This is our curve. And I'm going to draw it slightly differently. So imagine that, just stretch our axes a little bit, because I want it to look a little bit like this. All I did was just change the scale. Don't worry too much about it. So this is an equation of degree 3. The procedure we had before, if you remember the procedure, we had this idea that if you find a point, you pick a line, you project. You project, and then the other solution was rational as well. But the trick there was because the equations were all quadratic equations. And when a quadratic equation has one rational solution, so is the other. But here we're going to have a cubic equation. That's not going to work. Here's what does work. Suppose we have one rational point and another rational point. Suppose we guess 2 solutions. What we can do now is draw this line. And it intersects the curve in a third point. Right? Now, when we write down the equation of this line and we solve for the line and the curve put together, we're going to get an equation of degree 3. It has 2 rational solutions. Then so is the third. For the exact same reason as before. If you have a polynomial equation of degree 3 with rational coefficients, everything here is rational coefficients. You see why? This is y squared equals x cubed plus 17. Everything here is integers, even, not even. Definitely rational, right? This line is defined by 2 rational points. So its slope is rational. And it's, what do you call this b thing? Y-intercept. It's also rational, right? So this is going to be a rational line cutting a rational curve. So we're going to get a cubic equation of degree 3. It has 2 rational solutions, then so is the third. For the exact same reason we talked about before. The sum of the solutions is a rational number. 2 of them are rational, so is the third. Right? So in the case of this curve and other curves like this, of degree 3, what we get is a procedure for getting from 2 solutions a third. It's like an addition law. It's like algebra. We have the first point, call it P1, and the second point, call it P2, and this third point, we can call it P1 crazy plus P2. It's a way of adding two solutions and getting a third. The whole theory of number theory of elliptic curves is based on this observation that there is an addition law for the points on the curve. Very important. Now, what do we do if all we have is a single point?
Use the second one.
Which one?
The Mr. Bush.
Yeah, we're trying to figure out Mr. Boucher here. We're not going to try to assume here. We're trying to see what he does. So if I have 2 points, I can connect them and find a third. If I only have 1 point, what can I do?
You can create, like, just take a, like, 0, 0, and, like, pass
0,
it
0
through that.
is here. It's not on the curve.
Right, I know, but, like, pass through that.
That's a good thought. If we did that, we're going to have a line here, which is a rational line, because it passes through a rational point and another rational point. And it's cutting our curve in maybe 3 points. I'm not sure.
Yeah, probably.
Right? One of them is rational. This one. This one is rational, but it's not on the curve.
But you can use it to find the third point. It's
Wait,
on
wait.
the zero.
So all we have now is a curve and a line intersecting in 3 points, one of which is rational. Can we say anything about the other two?
No.
They could be rational, they could be irrational. But what
If you go to the origin.
this is the origin, but it didn't help because it's not on the curve.
So we have 1 point on the curve, and we're going to figure out a way to get another.
Yeah, so the trick is this. We know how to add 2 points. What if I keep this point fixed and bring this one closer and closer together? What happens to this line? What does it become in the end?
The tangent.
The tangent.
Sure.
What happens to the tangent line? It's almost the same line you suggested, but the tangent line here, it's strange, right? It's intersecting the curve in only 2 points. Here and here. What is this intersection called? It's a double intersection.
Right. Multiple.
This line cuts the curve twice at the same point. This is what tangent means. When you take 2 points in a curve, you take the line between them and you bring them together. In the end, you get the tangent line, which kind of cuts the curve twice at the same point. If you solve this algebraically, what you're going to get,
Is that the same thing as like
Is
a
this-
multiplicity of two?
you get a cubic equation which has 3 solutions, 2 of which are the same. Just like in the quadratic equation case, if your parabola looks like this, right? This is a double solution. You use the formula, the discriminant is 0, right? You get the same solution, same point. So if we have any x, sorry, if we have any solution x, y, some x, on the curve, which happens to be rational, here's the geometric procedure to produce another one. Find the tangent, find this equation. It's not very hard. You do the derivative, you take the slope, you create the line, and you find the third point of intersection of the tangent with the curve. There's going to be one. Because it cuts here twice, and there's going to be another point where it cuts the curve. And by the reasoning we had before, that's going to be a rational point as well. So if you go through this the same way you did earlier today, with the circle and the point, you're going to be able to find another point in green with some crazy formula for its x and y. Guess which formula is that?
Can we do that?
You can. I think we can leave this for our homework. But here's the funny thing, though. Mr. Bachet found this weird formula by trial and error, as far as we can tell. We tried and it didn't work, and tried and it didn't work, and tried again. All of a sudden, boom! He found everything just magically worked. Seriously, as far as we can tell, that's what he did. If he had known analytic geometry, either he would have realized, or maybe that's a much easier way to do this, right? Because all we're doing here is just taking a point, finding a tangent, getting another point. It's called the duplication formula. It's called the duplication, but this is P1 plus P2. This is P plus P. It's adding the point to itself. It's doubling the point.
Now, can this be extended to do rational solutions of any cubic curve?
Yes. Yes. So, let's see. The equation x cubed plus 17 is a little bit unrepresentative geometrically. I don't want to erase this, so I'm going to keep that. I'm going to do it here. Many other elliptic curves. So, what does a general cubic look like? It has this valley and mountain, right?
Yeah.
So typically it may look like this. You take the square root of that, what do you get? So here you get nothing. And here you also get nothing. Here in the middle you get the square root of the positive number. There's two values, right? So we'll get something like this. And here we'll get something like this. This is generally what an elliptic curve looks like. Now this doesn't look very illuminating. It's like an ellipse. This is an ellipse. It's a cubic curve, right? It's not this kind of oval and this kind of slopey thingy.
It doesn't come to a point at that right intersection?
Here? Where?
You know, you drew that black line in with a curve there.
Yeah, because
Is it not?
here there's no square root, but here there's two, right?
Like this.
No, I get why there's a positive and negative, but I'm asking, should the curve be shaped
more
like?
Pointy?
Yeah.
No, not pointy. In most cases, when it's non-singular, it's going to be smooth. You can check it out.
Yeah, I will.
This picture is misleading in two ways. One is there's a point at infinity here, which we're not seeing. Did you guys do projective geometry in the circles, or? Well, in projective geometry, we take infinity and we'll bring it back to the finite. So what really this is that there's an oval here, and this is another oval. This point is infinite. Because this point is infinite, when we look at this ordinarily, it's going to get thrown to infinity, but it's really here. So what this is, it looks like an oval and a line, but it's really an oval and an oval. The other thing we're missing here is that we're doing everything here with real numbers. We are already smart people. We know that the right way to look at stuff is complex number, right? Because otherwise, solutions have many more equations. Equations have many more solutions when we look at complex numbers. When we look at the complex numbers, you know what this is?
A line.
Does this look like a torus?
Donut.
Torus, the donut. This is a donut in two-dimensional complex space. Because we have such a narrow vision, we're slicing it with our real plane, because all we know are real numbers, right? So we slice it, and we get these two ovals. And the other problem is we're missing infinity, so we don't need to look at two ovals. But in
So
reality,
When you say two-dimensional complex space, you mean something that's four-dimensional then?
yeah,
Is that's what you, just want to clarify.
this is two-dimensional complex, and we're cutting it with a two-dimensional real line,
Mhm.
right? And we're getting this. So just so you know, elliptic curves, that's what they look like.
But they don't really look like that.
Sure they do.
But that picture is of a three-dimensional object.
Well, it's a two-dimensional curve. It's a two-dimensional surface.
Right.
Happens to be situated in two-dimensional space. It's really in four-dimensional space, but it doesn't matter. It's still two-dimensional.
Okay.
Nothing is missing from
Right.
this picture. The ambient space has one more dimension, but who cares?
Okay.
The thing is really two-dimensional. Well, it's not as symmetrical as I may have drawn it. Maybe who cares?
Ambient space doesn't feel like
It really is a torus. No, I swear to God. These things are really toruses. We're just, when we're looking at the rational solutions, it's okay to look at them like this, or like this. Now,
So you're saying all elliptic curves are really toruses?
yes. All elliptic curves are everything that has, well, generally they look like this. We just looked at one example, which was x cubed plus 17, but you can plug any numbers you want here. Almost any numbers you want. But you don't want to have this thing have repeated roots. If this thing has repeated roots, then it degenerates, because, for example, if our original green line here looked like this, you know what would happen here? Just what you said. There's going to be a pinch, or there's going to be a singularity. There's going to be something that doesn't look smooth. Okay? So this should not happen. But that's rare. You don't have to worry about it. Generally speaking, these guys look like this, and in complex projective space, projective because we need this point in infinity, they look like a torus.
So that picture, the two ovals compared to the donut, you're basically taking the two ovals and then like coming out from the board and meeting the other one.
Yeah.
And so you're saying, but then what happens in that one? Because that one only has one oval.
The problem with that one is there is really a torus, but we happened to unfortunately slice it like over here. Like imagine you have a donut. You have a donut, and you're taking a knife and you're only chopping it like here. So unfortunately, this torus, its intersection with the real space is very small, just one oval. So this thing really is an oval because we're missing the point in infinity. But so usually when you cut a torus in two, you get two ovals. Sometimes you're unlucky, you get just one. But if you complexify and projectivize, it's a torus, right? And this law works on the whole torus. Like on this torus, you can take any 2 points, add them up, and find a third. And this is the addition law on the elliptic curve. Now, the point I was trying to make with I'm trying to make a few points with all this. One is, doing number theory very often becomes much more clear, much more obvious, much more meaningful when you're looking at things geometrically. This is a number theoretic formula. It takes a solution which is rational, and it spits back another solution which is rational. It's a magical formula. It's really hard to do. If I didn't give you this formula and I would ask you to find it, I don't envy you. It's really, really hard to be able to produce more and more rational solutions. By the way, if you want to play with this thing later on, these whole number solutions are not the only ones. If I remember correctly, this equation, the 17 here is judiciously chosen. This equation is 8 or 9 whole number solutions, not rational, whole numbers. If you take these solutions, you plot them, and start drawing these lines and these tangents, you'll find more. It takes a little bit of work, but you'll find more. So, just to explain what I mean by that, so I'm going to draw this again. It's too kind of this. So we have our curve, which looks like this, right? And we have some point on it. -1, 4, 2, 5, -2, 3, and 4, 9. Right? We have these. We found 4 points already. We actually found 5 rational ones among the ones that were here before. So I can now start playing with this construction, this called the chord and tangent method. I can take these two, connect them together, and find another one. And then I can take this one and that one, connect them together, and find another one.
Those are not whole number solutions, though.
No, typically they would always be rational.
Right.
Guaranteed to be rational. Typically they won't be whole number solutions, but sometimes they will. And in this particular case, because again, 17 was judiciously chosen, not by me, it's a whole classic topic, you're going to get plenty of them. Like sometimes you'll get a crazy rational number, but sometimes you'll just add 2 of these together and boom, you'll get another one. I think one of the whole number points is actually pretty big numbers. Like x is, I think, hundreds or something like that. So this curve has infinitely many rational points and only finitely many whole number solutions, integer points. That's very, very typical. It's always the case that there's only finitely many integer solutions. It sometimes is and sometimes isn't the case. There's infinitely many rational points. So contrast this with the circles. We've seen 2 circles, one which had nothing, and one which had so many rational solutions it was kind of dense. One circle, it's covered the whole circle. Here it's completely different. The rational picture here can be empty, can be a few discrete points, can be infinitely many points, but they're not dense. They're like splattered all over the place. Sometimes there's multiple infinities of points, like in families of solutions. What time?
15 minutes.
is a big topic. Early in the 20th century, it was proved that you can get all the points, all the rational points on the curve, starting with finitely many and doing this thing. So if you are very fluent with your chord and tangent method, and you want to find all the points, you have to start with just a finite number of shrewd guesses, and then you can get them all. It's non-trivial. It's a very, very non-trivial theorem. It's called Ordell's theorem. And some of you have mentioned, and I think you've heard this, Fermat's last theorem. Remember that? What it says is that this has no non-zero solutions when n is more than 2. Remember that? You see that? In our language, we can divide this by c to the n. And this is a over c to the n plus b over c to the n equals 1. These are rational numbers. So let's call them x and y.
Yes. Yes.
This is a curve, just like the curve that we have studied today. For example, if we take n equals, I don't know, 10. X to the 10 plus y to the 10 equals 1. What does this look like, you know? It's almost like a circle, but power is 10 instead of being power 2. It's like kind of a bloated circle. Looks like this. And what is Mr. Fermat telling us? What are the rational points on this curve?
There are none.
There are none. So you see that the Fermat's theorem fits very nicely with this schema of diaphantic analysis that we've been looking at. There's a curve, a very simple one to behold, nothing fancy, and we're just claiming that it has no rational points whatsoever on it.
To be fair, there are 4.
Sorry, except for these trivial ones. Well, you take x equals 1 and y equals 0. So the trivial solutions to that, right? Now, this is not a cubic equation, right? Everything I said so far about this addition law and Mr. Bachet and all this stuff doesn't apply here. Equations of higher genus are very hard to tackle, and we don't know how to do this. In the late 80s, somebody called Gerhard Frey suggested a method of approaching this problem with these things. That was a big surprise, because these don't look at all like elliptic curves. But he said, well, if you have a solution to that, we're going to construct this strange elliptic curve from it, and this elliptic curve will have very strange properties. So it shouldn't exist. And then someone proved it really shouldn't exist, and then someone proved that strange properties really cannot happen. And wow, this is how Fermat's theorem was eventually solved. So the point is, elliptic curves, the cubic equations, are like a level of complexity that we can kind of understand. The conics are easy. We did the conics today. The higher power equations are very hard. If you're lucky, like Gerhard Frey was, you can find a clever way of translating this and back into the cubic realm. Then we have a lot of machinery to handle those things, but it's very complex machinery. It took 7 years for Wiles to 9, I think, to really finish up this part. But today we know that this equation really doesn't have this. Well, this one was known for a while, but for any n greater than 2, there's no non-trivial solution to this one.
What if you have the two variables and they're both cubed? Then you're still in cubic. Can you use this method of
This
crazy
one?
addition?
Yes. So this is a cubic curve. It's not of this form. You can make it into this form just by a simple transformation of variables. I'm not going to show this now, but the reason I wrote down this formula, in general, you can start with anything like ax cubed plus by cubed plus cx squared y plus dxy squared plus ex squared. Like you can start with a general cubic formula. All the different combinations of variables you can make up to the 3rd degree But then, by making clever substitutions like let's replace y by y minus something, and do stuff like this, you can simplify it until you get to this Weierstrass normal form. You can always get to this form. That's helpful. It's not solving the problem, but this is why people look at elliptic curves usually like this. But you don't have to. This is perfectly fine.
But the curve would look different, right?
It will look different.
And then you don't have that.
It's still a torus.
It is?
Yeah, always a torus. It's just sliced differently. It's gonna look the same, eventually.
Okay.
It could be like, this, for example. Or just like this. This particular one, what does it look like? X cubed plus y cubed equals 1. What does this look like? Can you guess?
So you have a negative
the key difference. The key difference between this one and that one is that here, because the degree was even, you can't make the numbers too big, because this is just like extracting a square root. If x is too big, it's not going to work. This doesn't work here. So this, I think, looks like this.
Wait. If you just move the x cubed to the other side, you have 1 minus x cubed. So you have x cubed, which does this, and then you flip it negative, move it up 1, and then you take the cube roots and just make the number smaller. So then shouldn't it go from the top left to the bottom right?
It does.
No, the other way.
The other way around?
Yeah.
No. Wait.
Yeah. Yes, that's correct.
So you're saying...
So just change it to y cubed equals 1 minus x.
Yeah, let's keep it this way. You're saying it looks like this.
Something like that.
Yeah. But it's not like that. My point is, it's the same thing as this one, only rotated. See what I mean? But it's not fundamentally different.
Right.
It's not fundamentally different.
Or rotated and flipped, right?
Rotated, flipped, stretched, what have you, but it's not fundamentally different. And if you look really hard, it's a torus. It's just hidden.
Can you draw the
Hidden
oval?
because you're missing a point. There's always an asymptote here,
Yeah.
which is the point in infinity. So this really is just that, the point blown off to infinity.
Okay.
And outside of this thing is a big torus, which you just happen to slice with your real plane in an unfortunate place where you just see one over. It's always a torus. I think I owe you one thing though. Sim Fermat. Simplification formula. One?
Were you doing Pythagorean triples?
Oh, exactly. That's right. That's absolutely right. So remember this formula we had?
Yeah, not
Remember this one?
Yeah.
Now t is a rational number, right?
well, this one is.
Right? No, I'm going to call it. I'm sorry. I'm going to call it u over v. And so if you substitute u over v into these equations, what do you get? Do we have time for it? Yeah, do it. We have a few minutes.
Candy already knows.
Hmm?
I know, but I lost this.
Write t as u over v. U and v are now whole numbers, fractions. Okay? You can assume that they are relatively prime, because you not just take away the factor. Plug those in here. Come on. You got a few minutes. Just plug u over v into these formulas. Tell me what you get. Thank you for reminding me. We should have done this. I'm going to do it. skipping some steps here, but I know that it's not hard.
Right.
This is what you start with. Expand it out. Get this right.
Well, I got those,
Yeah,
but
we
what are
got
you doing on the right?
This
It's just
Just
justifying.
You're showing the work?
an intermediate step.
Oh, okay.
I like.
I'm not cheating. I've actually done this in my head. Did you get it, you two?
Yeah.
Now, so this is x, and this is y. What do we know of x and y? We know the squares add up to 1, right? So if we add these two, we're going to get v squared minus u squared over v squared plus u squared plus 2uv over v
Squared.
plus u squared
Each thing squared.
equals 1. Or in other words, if we multiply out by the denominator, we're going to get that v squared minus u squared squared plus 2uv squared is v squared plus u squared squared. Now, first of all, this is very easy to verify. If you're not sure, just expand this thing out and it just comes falls out. It works, right? This is a Pythagorean triple. This is x, this is y, this is z.
And now we can generate.
So pick any two numbers v and u with a caveat that I'll mention in a second.
V is bigger than u, yeah.
Define x to be this, define y to be that, define z to be that, and there you go. There's your Pythagorean triplet. This generates all Pythagorean triplets. You know why? Because the procedure I showed you before is guaranteed to cover all the rational points in the circle because you can invert it. If there is any rational points on our circle of radius 1, and we connect it to our minus negative 1, 0, this is going to come with a rational point. So we didn't miss anything. This procedure gives you all the rational points in the circle, and the rational points in the circle are all the Pythagorean triplets. Because any Pythagorean triplet, if you have x squared plus y squared equals z squared, just divide by z squared, and you get 1. Any Pythagorean triplet gives you a rational point in the circle. Just as simple. Different names are the same thing. So there's a little bit of a tiny wrinkle here if you want to guarantee you're not getting the you can get the similar triangles like multiple times. If you want to make sure this doesn't happen, choose u and v so that they are not both odd. They should be relatively prime and not both odd. It's a quick calculation, very easy to do. So the way to generate all the Pythagorean triplets in the world is to pick u and v to be whole numbers, relatively prime, not both odd. Define x to be this, y to be that, z to be that, and there you go. So the geometric method of projecting from a rational point on a line gave us a very methodical way to find all the Pythagorean triplets. And the same procedure, your homework, by the way, if you remember, one of your stuff was to do this. Remember the other circle? Right? This will give you a general solution to the variation on Pythagorean triplet, which is this one. If instead of a squared plus b squared equals c squared, you want to solve a squared plus b squared equals 2c squared, it's a different problem in number theory, but you're going to solve it. You're going to get all the solutions with the exact same method. You can also get a solution to this problem. A squared plus b squared equals 3c squared. Remember, we did this too. What are all the solutions to this one? There aren't any. It's the easiest equation to solve. This has no solutions. This has infinitely many, just like the original Pythagorean triplets. So we've done a bunch of stuff today. So let me just trying to remind you everything we did. We started with the circle. We looked at the formulas for the circle which were familiar to you. We then created another one which was hopefully unfamiliar to most of you. And gave us the rational parameterization of the circle. With it, we found all the Pythagorean triplets in the world. And then we also took a detour to Dirac-Kaplan analysis and looked at what this whole thing is if we go 1 degree higher into cubic equations. We saw that some magical formula found by a French guy in the 16th, 17th century can be easily explained geometrically. And this led to like a flourishing of like the whole topic of elliptic curves and the addition law and Model theorem. Many, many wonderful things. Maybe I'll tell you about when I come here again. Thank you. Questions? You're still not sure about the descent argument?
I'm sure about so many things.
Yes, questions?
So are there other applications of this? I mean, obviously this is pushing the envelope from quadratics to cubics. So it's very interesting, but are there like really concrete applications?
Yes, there are very, very concrete applications of elliptic. Funny enough, early in the 20th century, nobody thought the answer to this was yes. G.H. Hardy, who was a number theorist and analyst, famously said that like he likes math because it has no applications. He was kind of a pacifist and he didn't like stuff. He liked math. But he was wrong. And today, elliptic curves are used in cryptography all over the place. So like public key cryptography, if you've heard about this, the methods for factoring large numbers and methods for finding very large primes, which are used all over the place in e-commerce. So whenever you buy at Amazon, there's an elliptic curve working in the background, picking your prime numbers for you. I won't have time to talk about this today, but I can talk about this next time. Elliptic curves, other applications. Probably the big one. Probably factorization. Yeah, that's probably the one real-life application that I'm familiar with. Number theory generally doesn't have any applications. And that's fine. I'm with Hardy with that.
Except its one application is like the biggest, heaviest application in the world.
It's pretty big.
Yeah.
What is that?
People keep saying that if we, I don't know if I buy this, but people keep saying if we understand elliptic curves a little better, or if we prove the generalized agreement hypothesis, stuff like this, then all of e-commerce would crumble down. Then all of our encryption would disappear. I don't think that's actually true. Those theoretic arguments don't necessarily mean that we can actually do any of those things. But yeah, to some degree, our activity on the internet is governed by our ability to. Do you know what a public key is? So in encryption in the old days, what is encryption? It's like locking something, right? So you have a lock and you have a key. And if you wanted to encrypt something, you had to have the key to lock it. The other person, on the other hand, had to have the key to unlock it. But if you know those locks you can buy, and to lock them, you don't need a key. You know these locks? You only need the key to open them up. That's the idea of public key cryptography. Like I can publish my keys, and I can. People can encrypt messages and send them to me, and only I can open them, which used to be a very bizarre notion because, like, if you can encrypt, you can also decrypt. Like, it's symmetric. The public key is not symmetric, so anybody can encrypt. So the point is, you go online, you're anonymous. You never agreed with Amazon that your encryption key should be 75543. You never went to Amazon and said, "Here, keep it now." You never did that, right? It's automatically generated for you, and it's still safe. That's the magic of public key cryptography. There's an encrypted line between you and Amazon, between you and wherever you buy stuff, but you never settled on the key. That's public key cryptography, and it's based on a variety of schemes. Some of them are based on prime number factorization, and to find big prime numbers, we use these key numbers. It's very vague, I know, but I won't be able to do much more than that now.
What is the heavy application?
Well, that's what I mean. That it's used. You know, like a million times a second now,
Yeah.
and
It's
also it's the big problem that the NSA has.
Yeah, it's the largest employer of mathematicians.
Because the NSA deals with the problem that the bad guys can encrypt their messages most likely more easily than the good guys can decrypt them. And so there's this giant struggle about finding prime numbers and all the machinery around it.
There's another application of elliptic curves, I just remembered. There's something called encoding, which is different from cryptography, which is what you do on a CD or information transmitted from like satellites and stuff. you're sending information, sending bits, and you want to help them be received on the other end correctly. So you add those extra digits that kind of checksums, so that the other end can either know that something was misreceived or something's going to, you can correct the error. And there are very, very good codes. These are called codes. They're not codes in the encryption sense. It's almost the opposite. It's code that helps you transmit information so that it's legible. There are very, very good codes based on elliptic curves. I don't think the other ones used very commonly in applications today, but there are fantastic codes that use elliptic curves to operate. What else?
Can I ask one more question?
Yeah, sure.
So pre-projectification, like if you look at y squared equals x cubed equals 17 on C2, what is it before you compactify it?
It's a torus that just in this case the compactification just adds 1 point.
Right.
That's all it adds. So just take a torus, pinch a hole in it, take the hole and just rip it up.
Okay.
So it looks like a donut that has this whole gaping hole that goes into infinity, right? That's what it looks like. So the compactification piece doesn't change much. It's just a single point that you're missing. The moving from R to C changes like the dimension. So instead of a curve, it becomes a surface. That's a big deal.
So if we were to do like more readings of this, anything you suggest, and this is
I've learned quite a bit of number theory before I stumbled on this book, which really helped me kind of get a coherent picture. So this is a really good book. I really like it. Rational points on elliptic curves by Silverman and Tate. It doesn't assume a whole lot. It goes through everything I said today, and a lot more besides. I think it thinks you know group theory a little bit. When it gets to this addition law and Mordell theorem, maybe it defines group. I'm not sure. It doesn't assume a whole. I think that's probably the book that assumes the least of its readers in this domain. This guy Silverman wrote other books on elliptic curves. Don't touch them. They're really hard. This guy Tate wrote a lot of stuff on number theory. Stay away.
well, the intersection field too makes it.
Yeah, together they wrote this very nice. But what else?
John Stillwell's history books
He talked about
touch upon this whole circle of ideas, I think, in a way that's
More accessible.
well, and it's designed to be for college undergrads.
Which one? The history of math?
Yeah, math and its history, and then also his version of number theory. I forget the title, but it has something like number theory in its title.
There's a book by, I'm almost hesitating to recommend, a book by a guy called Neil Kovitz about elliptic curves and modular forms. What this book does very, very nicely, it takes a very concrete problem called the congruent number problem, which is a classical problem from antiquity, and it shows you how to solve this thing using elliptic curves and modular forms. It gets really hard very quickly, so it's not like fun reading, but it's interesting to see how another problem from antiquity had to wait more than 2,000 years to be solved using these tools.
But an interesting question is there a true popularization of this? And I don't think there is. There's all these books about Fermat's last theorem, and I don't think any of them are.
I'm pretty sure they touch upon
Yeah.
curves when they get to like the approach of Farai and Serre and Wiles.
Jim Propp wrote a book about Fermat's last theorem, but I don't think he ever finished it. But because
there's a book by Yves Allegoire about the mathematics around. Oh, there's Stewart and Tall. Maybe Stewart and Tall. Look up a book by Stewart and Tall. It's called something like The Mathematics Behind Fermat's Last Theorem. It's a pretty popular book. It does have elliptic curves in it. I don't know how deep or how much. But maybe it's not a good option. This one I'm if you really into it. Elliptic curve of modular forms. Yeah, that's what. Well, let's see. What about? I'm not even sure what's a good book to just do the rational parameterization of cones. Other than this one.
Stillwell has enough to get you started.
Silverman and Tate do
Yeah.
what we did today with the circles. They do it like in page 10. But still, it's there.
Yeah.
It's there and yeah.
Yeah, I know Stillwell. He does a lot. I think several of his books have good rationalization of the circle as sort of a starting point for going in different directions. So that might be the easiest choice. But there was this great book about Fermat's last theorem that came years ago called, I think, The Unfinished Theorem or something like that. So just a book for lay people. And it was really great. It was way before Fermat's last theorem was resolved, and I don't think there's anything as fun to read since Fermat's last theorem was solved.
Really?
Yeah, you could write it.
The unfinished theorem.
Something. It had names something like that. Yeah, the last theorem maybe is what it was called. Yeah.
Funny name. Modular theorem for many years was not a theorem at all.
Yeah.
Conjunction. We'll call it a theorem. Alrighty, thank you folks.